Okay, in this section 14.2, we're going to look at the effect of the concentration of reactants on how fast the reaction proceeds, which of course is the reaction rate. We're going to use a technique called the method of initial rates, very standard type of problem in kinetic analysis. So let's take a look. In general, when you increase the concentrations of reactants, that tends to make reactions go faster. On average, the closer the molecules are to each other, the reactants, the greater the probability they are going to collide with each other and form products. So as you increase the concentration of the reactants, it tends to go faster. Now, there are some exceptions to that. There's some reactions where that's not the case, but generally it's true. So here's an example of a reaction where we have nitric oxide, NO, and it's reacting with H2, hydrogen, and it's forming ammonia and water. And there's something called the rate law. The rate law is generally of the form rate equals, so the rate on one side equals, and then on the other side, it's going to have a K, a lowercase k. Sometimes the K will have like a subscript like K1 or K2. Sometimes it has a superscript like K dash or K prime, that sort of thing. But it's just a lowercase k times the concentration of the first reactant raised to some exponent times the concentration of the second reactant raised to a different exponent. So notice for this reaction, there are two reactants, NO and H2. So in the rate law, there are two materials, two reactants using bracket notation. Of course, the bracket notation refers to molar concentration. Now, we're going to go through why this is important as we go through, but it essentially tells us that as you change the concentration of a reactant or both reactants, that will change the rate of the reaction. If you want the reaction to go faster, one way to make it go faster is by increasing the concentration of the reactants. Maybe one of them, maybe both of them, maybe neither of them. But you may want to do that. Now, if there's more than two reactants, we would just multiply by a third term. So concentration of the third reactant raised to some other value, maybe Z would be the exponent. If there's only one, let's say there was only NO as a reactant, then we would just have K times the concentration of NO to its exponent. So K is called the rate constant. It depends on temperature. So if you change the temperature, usually K will change. But if the temperature remains constant, you can use varying concentrations of reactants and it'll still have the same value of K. Okay? Depends on the reaction, depends on the temperature. The units of the rate constant, we'll get into that a little bit later. It sort of depends on what the equation looks like. So it depends primarily on what those exponents are, whether they're a 1, a 2, or a 3. And again, these exponents, x and y in this case, are called orders of reactants, orders of the reactants. That term order comes from algebra. When you have a polynomial, y equals ax squared plus bx plus c, for example, that would be a quadratic. Polynomials have coefficients. They have the constants in front of the x, but they also have the exponents, right? The exponents like x squared, x to the first, x to the zero. Those exponents are often referred to as orders, okay? And the terminology that we use is if the exponent is a zero, we call it zeroth order. So here's an example. The rate of the reaction equals the rate constant times the concentration of the reactant A. So in this case, A is a reactant, raised to the zero. Now, interestingly enough, if you take a number and you raise it to zero, you generally get 1. So that means that whatever you change the concentration to, you're still going to get 1 for that value because 1 raised to the 0 is 1, 2 raised to the 0 is 1, 0.2 raised to the 0 is 1. So in that particular case, the rate just becomes k because k times 1 is just k. So the rate constant is actually equal to the rate in a zeroth order reaction, and that does happen. If the exponent is a 1, we call that first order. So rate would be equal to k times the concentration of A. If it's second order, that means that the exponent is a 2, and we would say that the rate is equal to k times the concentration of the reactant squared, and so forth and so on. It is possible to have fractional orders, so you could have to the 1/2 power or 3/2, but generally we don't worry about those in this course. We're just going to look at the ones, for the most part, we're going to look at first, second, and third. We don't really even going to talk about zeroth, but that does exist as well. Okay. So the main thing we're doing in this section, aside from just introducing some of this terminology and pointing out the importance of the rate law, is we're going to try to figure out what these exponents are from experimental data. So the first example we're going to look at is with NO and H2. That's the reaction we just mentioned. The rate law would be K times concentration of NO to some power times H2 to some power. Those are molar concentrations. And what we want to do is we want to find out what these orders are. What are these exponents? And so notice the way this is set up. Here's a set of data. There are 3 experiments. A trial is essentially an experiment. So there's 3 experiments, 1, 2, 3. And what you'll see is if you look at these numbers is in experiment 1, the concentration of each reactant is the same, 0.2 molar. And then we have an initial rate. The rate at the beginning of the reaction is 0.4 molar per minute. In trial 2, the concentration of NO is now doubled, but the concentration of H2 has stayed the same. And look what happened to the initial rate. It increased. So what we would conclude from that is the reason the rate got bigger, increased from trial 1 to 2, is because of that concentration of NO changed, right? Went from 0.2 to 0.4. That caused the rate to go faster. Now, in experiment or trial 3, the concentrations are back at 0.2 for NO, but now H2 is doubled to 0.4. And now finally the initial rate is 0.8. So it's sort of in between these two rates. So a little bit slower than trial 2, but faster than trial 1. Okay? So what we want to do in this example is we want to figure out what the values of x, y, and k are. And I'm going to show you a method for doing that. Again, it's called the method of initial rates. So let me bring up the whiteboard and we'll do that. Okay, so here we go. So again, we have 3 trials, right? 1, 2, and 3. And then we have concentration of NO, and that was zero point 0.2, zero point 0.4, and then back to 0.2. We also had concentration of H2, and the concentration was 0.2, zero point 0.2, and then 0.4. And then we had our rate, which was in molarity per minute. Not per second, but per minute. Typically, we would do it per second, but in this case, it was per minute. So 0 0.4, 1.6, and then 0.8. Okay. So here's the method of initial rates. This is just one way to do it. But what I'm going to do is I'm going to look for 2 experiments. I'll start with NO. It's arbitrary which one we start with, but I'll start with NO. We're going to look for 2 experiments, 2 trials, where NO's concentration is different, but the other reactant is the same, doesn't change. And if you look at the 3 trials, that would be 1 and 2, right? If you look at these 2 right here. The NO in the first experiment is 0.2 molar, but in experiment 2 is 0.4 molar, changed. But the H2 stayed the same, right? Didn't change. So that's what we're going to do. And what I'm going to do is I'm going to look at the rates and compare them for those 2 experiments. So for experiment 2 and 1. Notice that for experiment 2, trial 2, the rate is bigger than it is for rate 1 for the first trial. It's 1.6 instead of 0.4. So I'm going to do a ratio. So the first thing you do is you do a ratio of the rates. Ratio just means one divided by the other. So I'm going to take rate 2 over rate 1. By the way, it'll work if you do rate 1 over rate 2 as well, but it's a little bit easier if you take the rate that's bigger and divide it by the one that's smaller. So 1.6 divided by 0.4, right? I'm just taking these numbers for the rates, dividing them, and that gives me 4. In other words, trial 2 has a rate of reaction that is 4 times greater than rate 1. It's 4 times as fast. Easy enough. But we also have this thing called a rate law, right? So the rate law looks like this. Rate equals K times concentration of NO to the X times concentration of H2 to the Y, right? And these exponents are generally either 0, 1, 2, or 3. Most commonly, they're 1 or 2. And what we're trying to do is we're trying to figure out those values. So here's what I'm going to do. I took initially rate 2 over rate 1. I'm going to do the same thing with the rate law. I'm going to take the rate law for trial 2 divided by the rate law for trial 1. Because remember, the rate equals the rate law. So if I do, if I say A equals B and C equals D, and then I do A over C, B over D, right? A over C would equal B over D because A equals B and C equals D. So same thing here. So what I'm going to do is I'm going to take the rate law for, just like I did before, for trial 2, divided by the rate law for trial 1. And I'm going to use the numbers that are in the table. So for trial 2, we don't know the value of the rate constant, so I'm just going to put K. Now, for number 2, NO is 0.4, so I'm going to write 0.4, and that's going to be to the X. And then hydrogen is 0.2, so 0.2 to the Y. Okay? So I'm just plugging in the numbers that are in that table. And then I'm going to do the same thing for rate law 1, K. Now for trial 1, it's 0.2 molar for the NO, and it's 0.2 molar for the H2. And now I'm going to use some reasoning. K is the rate constant, and we have it in the numerator and the denominator, so we can just cancel it. And then 0.2 molar for the hydrogen to the Y divided by 0.2 molar hydrogen to the Y. That's the same. It cancels, right? So it becomes 1. So this simplifies. I'm just going to abbreviate this RL2 over RL1. Would be 0.4 to the X divided by 0.2 to the X. And one of the rules of exponents is that if you have a number raised to an exponent divided by a number raised to the same exponent, so X is the same exponent, then you can simplify this and write it as 0.4 over 0.2 in the parentheses to the X. Okay? So as long as it's X, if let's say X is 1, it'd be raised to the first power, raised to the first power. If it was a 2, raised to the second power, raised to the second power in both the numerator and denominator, you can do that. 0.4 over 0.2 is just 2. So this is 2 to the X. And our goal is to find out what X is. So how are we going to do that? Well, remember the rate is equal to the rate law, right? R equals. So if we did the ratio of the rates and we got 4, and then we did the ratio of the rate laws and we got 2 to the X, this now follows that 4 is equal to 2 to the X, right? Because R2 over R1 is the same as rate law 2 over rate law 1. And so now you just figure out what X is. So let's just plug in some numbers. Anything raised to the 0 with the exception of 0 is 1. So, 2 to the 0 would be 1. Well, 2 to the 0 does not equal 4. Let's try the next one. 2 to the 1, 2 to the first power. Well, 2 to the first power is 2. That also does not equal 4. So that means X cannot be 0 or 1. But what if it's a 2? I'm just going up 0, 1, 2, 3. If X is 2, 2 squared is 4. And that works. So this works for X. This suggests that X is equal to 2 because 4 is equal to 2 to the second power, right? And so that means we know that x is 2. So now what I can do is I can now write this rate law as rate equals k times the concentration of NO. And now I know that's a 2. So I've figured out one of the orders. Now I'm going to figure out the second order, the one for hydrogen. Okay? So with this one, I'm going to try to do the same thing. I'm going to try to find two experiments where the concentration of hydrogen changes, but nitric oxide does not. And if you look at that, let me erase this. If you look at this, then it will actually work for experiment 1 and 3, right? Because in experiment 1 and 3, NO doesn't change, but H2 does. So again, I'm going to do the ratio of the rate that's bigger divided by the rate that's smaller. So I'm going to do R3 over R1, and that's going to be 0.8 over 0.4. You don't need to put the parentheses in. I just am doing it. And that's equal to 2. Okay? Again, we're trying to figure out hydrogen here. Over here, we already figured out the nitric oxide, okay? And then the same thing, we're going to do the ratio of the rate laws for experiment 3, experiment 1, trial 3, trial 1. So rate law 3 over rate law 1 would be K. Remember, rate law, you put a K in there. It's going to cancel, but that's okay. 0.2. Now, we actually know this number is squared, right? We already figured out the value of x earlier, so we can just put that in there. And then it's 0.4 for the hydrogen. Again, we don't know that yet. And then for trial 1, it's K times 0.2 squared, and then 0.2 to the y. Okay, that's going to cancel with that. As long as it's identical, same number, same exponent, you can cancel them, right? It becomes 1. K is a constant, K is a constant. That's going to cancel. And so now rate law 3 over rate law 1, that is going to equal 0.4. I'm going to actually skip a step and just go to 0.4 over 0.2. Remember, as long as the exponent is the same here, you can do the division in the parentheses and raise it to the same power. Okay? So 0.4 to the y divided by 0.2 to the y is equal to 0.4 over 0.2 to the y. Well, that's equal to 2, right? 0.4 over 0.2 is 2. So rate law 3 over rate law 1 is equal to 2 to the y. Okay, now let's come back. Rate law 3 over rate law 1 was 2. So that means 2 is equal to 2 to the y. Okay, what's going to work? 0 is not going to work because 2 to the 0 is 1. That's not equal to 2. 2 to the 1? Oh, yeah, that works, right? 2 to the 1 is equal to 2. So that means that y is equal to 1. Okay, now that means we can add this in over here. It is traditional not to put a number up there if it's a 1, right? Because if I were to say x, x is technically x to the first power, but we just write it as x. Same thing here, concentration of H2 to the first power. We've now figured out that this reaction is second order in NO, and it's first order, I'm abbreviating, right, in H2. In other words, if I double the concentration of NO, I will quadruple the rate. That's what actually happened from experiment 1 to 2. If I double the concentration of H2, that will double the rate. It's first order in H2. And that's what we figured out in experiment 1 compared to experiment 3. Now there's one more thing to do, which is to find the value of the rate constant. Okay. So I'm going to do that right here. And the way I'm going to do that is I'm going to come back to the rate law. Here's your rate law. Actually, let's use this one right here. And if I want to find K, I would just take R, which is on the left side, and then divide that by all the other terms on the right side. NO squared. And then H2 squared. I'm sorry, H2 to the first power, right? Because if I divide H2 divided by H2 on the right side, that becomes 1. If I divide NO squared on the right side by NO squared on the right side, that becomes 1. So the rate divided by these concentrations multiplied together is going to give you the rate constant. So in general, if you have multiple trials, what you would do is you would calculate each rate constant and then take the average of it, add them up, divide by 3. You might do a statistical analysis to see how close those values are to each other. For the numbers that are in this example, you're going to get the same value each time. Okay, so I'm just going to do it for one of them. I'll just do it for the first one. So the rate constant, K, would be the rate. I'm just going to do it for experiment 1. So I'll call it K1 because it's trial 1. The rate is 0.4 molarity per minute. And then I'm going to divide that by, in experiment 1, it's 0.2 molar squared times 0.2 molar for the H2. Again, this is trial 1. So if you take 0.4 and you divide that by 0.2 squared, and then you also divide it by 0.2, you should get 50. Okay? Now, in terms of the units, the rate constant units depend on what those orders are. So if I had 1 and a 1, I would get different units than if it was a 1 and 2, meaning the exponents. If you change the exponents, it changes the units. So we have to go through this molar in the top would cancel with that molar right there. So those molars are gone. So now you have molarity in the denominator. When it's in the denominator, we tend to write it as -1 because, let me write it this way. 1 over x equals x to the -1. That's a notation that we use a lot in chemistry. 1 over x squared would be x to the -2. Okay. Now, if you look over here, there's actually 2 molars here, so it's really to the -2. So let me see if I can erase that. So -2, right? Because you have this molarity squared down here, okay? And then it's per minute, that's up there at the top, divided by minutes, so minute to the -1. And again, if this were like a real experiment and we were doing it in the laboratory, there would be a certain amount of uncertainty in the values that we're getting, so they wouldn't work out perfectly. But for this particular example, if you do it for trial 2, you'll get 50. If you do it for trial 3, you'll get 50. So it's the same every time. But in reality, you would often see that they vary to some degree. Okay, so that's called the method of initial rates. And that is essentially a standard problem that we do in kinetic analysis. What it does is it allows us to determine the form of the rate law. Overall, this reaction is third order, second order in NO, first order in H2. So overall, 2 plus 1 is 3. And the rate constant is 50 reciprocal molar squared reciprocal minutes, right? We don't really make too much out of what the interpretation of the units are, but it's a third order reaction. And what this allows us to do now is to say, suppose I know the concentrations of the reactants, how fast will it go? I can now predict how fast the reaction will proceed because I know the value of K. I know how NO is in this equation, right? It's NO squared. So if it was 0.1 molar, it'd be 0.1 molar squared. And if it was H2 was like, say, 0.05, it would be times 0.05. So given the initial concentrations, or given the concentrations of both reactants, since we know the value of the rate constant, we would know the rate of the reaction. So it allows us to predict how fast this reaction is going to be. And so if I said, there's a lot of these reactants, it's going to be pretty fast. So there's only a little bit, it'll be slower. But notice it depends more strongly on the concentration of NO than it depends on the concentration of H2 because of that squared, right? So those exponents do play a factor in how important that particular reactant is in terms of how big the value of the rate is. Okay. So there you go. So there's our method of initial rates. And that's the main point, introducing the rate law and introducing the method of initial rates. That's the main point of this particular section, 14.2.